So it's a great pleasure for me to be here in Kyoto to do some lectures and to work in the project, the Unique Exchange. First I want to introduce a little bit about me and our company. In Germany it's typical at the University of Applied Sciences that you have two professions. One is to teach at the university and the other is to work in a company. And I'm working at Transolar Climate Engineering. We were founded in 1992, that means 23 years, it's a long time. And now we are nearly 60 employees and we're working in different locations. The headquarters is in Stuttgart, where we have two groups, one in Munich, one in New York, and since April also in Paris. And we are not architects, we are engineers, and we are not typical HVAC or MEP engineers, we are climate engineers. That's quite different, so I will a little bit explain with the project for you to understand what is the difference and why it is important to work together with architects and climate engineers for good comfort, for climate response building design. We're working on projects all over the world in different dimensions. This is our smallest house, 6 square meters, together with Renzo Piano architects from Italy. Mainly we work on office buildings, high-rise buildings. This is a very famous building in Germany. It's constructed I think 1995. This was one of the first climate response buildings. We did a lot of different buildings. Here you can see with Gary and partners at Basel, Novartis campus. We did some refurbishments and also project with outdoor comforts. I will explain a little bit about the Master City concept in Abu Dhabi. I'm working on a lot of projects with stadias, and and we're working also with artificial clouds. I will show it a little bit. So that means we have different projects, dimensions, but also different topics of the projects: housing, residential, office buildings, sports buildings, and so on. And in every design we have the discussion about climate response building design, or we call it green building design. But what does this mean, green building design? It can be a fake. Mostly it's a fake. Yeah? What is a green building design? A little bit flowers and so on. This is a green building design. But that's not the target, that's not the goal. The goal is to create a good comfort in your building, in outdoor and so on. And what are the aspects for this climate response building design? As we started with our company, our first goal was to save energy. That was very important. Save energy. But after some years, we recognized that to save energy is not so important. It's not the first thing in a design. The first thing is to create a good comfort. That's very important. And that's the first thing, the visual and the thermal comfort. Visual is daylight, also architecture and so on. This is the important thing. Because if you're a user of a building or you stay in front of a building, the first that we will say is not, oh, this building saves energy. No, the first will be, this is a good building. It has good design and it looks very pretty, and inside the building I have a good comfort. And then after some different points, the part energy is important. So that means we change our focus not to save energy first. First thing is to make a good comfort. So, what we are doing, we're taking advantage of natural energy sources, physical effects, that's very important. for good building design, for passive building design, and mostly we have to integrate different aspects like daylight, like glass quality, material qualities, and so on. So it means the main goals, optimization of our work is thermal and visual comfort, then to save energy, it's the second part, and last but not least, to minimize the investment in the operation costs. This is not a discussion in a lot of countries. I think it's the same here in Japan. The discussion about operation costs, there is no discussion because electrical power is very cheap. So, but I think you have to make a discussion about the thermal comfort. Yeah? We're in a building with a single glazed facade, with a very simple roof, I think so. And the comfort in the building, I think, is not always the best one. In winter, I heard it's cold here inside. So then the question is this the right design? Or is this the right material or the energy concept? So what our measures is to minimize the internal and external load. That means, for example, for external loads, solar loads, to have good glazing quality, to have a good shading device, and so on. Internal load, for example, artificial light, to reduce this power inside. And then the next step is to use renewable energies. This is not the first step, this is the second step. The first step is to minimize the loads, and we can do it by the optimization by dynamic simulations. We will make it tomorrow with some of the students here. This is a very helpful tool to analyze and to figure out what is the influence of the different concepts. So then you have the possibility to decide what is the right thing that you can do in the different steps. So the question is, what is comfort? Comfort has a lot of aspects. One is the temperature. That's true. But in this photo you can see, or you can imagine, the person lying here is well-being there because of the temperature, of the daylight, of wind, of the breeze, smells, and so on. But it's also clear that the person here don't want to work there. And if you have to design an environment to work very well, it's not the best one here. So we have to think about a lot of aspects about comfort. Also cultural aspects. I think this is a very funny slide. If you show this slide in Europe, everybody laughs and says, oh no, there is no place I want to go there. Too many people, crowd people, and so on. But I think in Japan it's not a real problem. I think so. And so there are a lot of other aspects you cannot measure. So that's very important. And especially for the buildings, there are some aspects you can measure. And this is very helpful to understand what is comfort. Comfort depends first on the daylight situation in the building. So that means if you have a lot of daylight inside the building, the people normally say, this is a good building. Also, a connection to outside. That means an open window is very important for buildings. Yeah, they can connect to the outside. But also to reduce the solar radiation is important, because the person sitting here is in radiation with the sun, so that means you have to shade the person. But in this way, you have to take care about reducing the daylight. Typically, you design a glazed facade, you have a shading device, and the artificial light you have to put on because it's too dark. So that's the point that doesn't help you to optimize the building. Other parameters are the air velocity and the turbulence of the air inside the building, the closing factor and the activity of a person. It's different. The person sitting there or making sports, that's quite a difference. And a very important aspect is the perceived temperature. The perceived temperature is not the air temperature in the building. It's let's say middle temperature of the air temperature and the temperature of the surfaces. That means, for example, in summer, you have a hot air temperature inside, but you have a cool surface, for example. You cool down the surface, the mid-temperature will be lower as the air temperature. So that means you have a higher air temperature, but you have a good comfort inside. The air temperature doesn't help you to analyze the comfort. The tools for this we use in our office is mainly a dynamic thermal simulation, so we can calculate exactly hour for hour the whole year what's going on in the building, what is the temperature, what is the energy consumption, what is the comfort. We use also computational fluid dynamics, CFD, to analyze the different temperatures in different layers. For example, this is the atria, and also the comfort aspect. And last but not least, the daylight analysis by simulation to optimize the daylight. This is always, let's say, a fight between a thermal optimization and the daylight optimization. To reduce the solar load, for example, you use a sun-shaded glass, but this reduces also the daylight inside the building. So to figure out these aspects, it's important to work in, we call it integrated design team. And not to fight against them, to work together. So that means the design team typical is, one is the architect, the mechanical engineers, the structural engineer, sometimes other consultants like physics and so on, and we call us the climate engineers. And we connect the different aspects of the different designers to combine it. What is also very important to think in different scales. That means we have to think from the master planning up to the city grid, up to the building, inside the building, to different rooms. It doesn't help you to think only about this one or about this one, because this has an influence of, for example, of a wind situation there. This has an influence of the traffic, for example, of this building. So that means you have to think about all these aspects. A very simple example is the aerodynamic shape of a car. Here you can see the development of we call the drag coefficient, beginning with 0.7, now we are 0.16, and the drag coefficient reduce the fuel consumption up to 50%. So that means nowadays the aerodynamic shape helps us to save energy. But if a system doesn't work, you have a very good car, but you stand in here. It doesn't help you to optimize the system. So that means you have to think about all. You have to think about the efficiency and the effectiveness of the whole system. And I think this is a very good slide to explain both together. The goal was here to design a very fast boat for a maximum of 12 people driven by wind, and this is the result. If you want to transport 100 people with a boat, it doesn't work. So that means the influence of the design is very important for the result. of the project. So, as a result of these aspects, we are thinking in 3 steps. And I think I can explain it very good with a triple jump. So that means every step is important, and the step after the next step is important. So that means the first step is the hop. And the first step in the design is to reduce energy. The second step, is the first jump, is to maximize the efficiency, and the third one will be to use renewable energies, step by step. And this is the first step, the second, and the third step. So that means first we made the building optimization, we can reduce the loads, we maximize the efficiency. In the second step, system optimization. And in the first step, you use renewable energies and substitute fossil fuels. So starting with the first step, we always do the site analysis. You have to do it, for example, for the weather there, for temperature, solar radiation, wind, and so on. And this helps you in the first step to think about what is the best material. For example, you design a building in the cold climate or in the hot climate, the design will be quite different, or should be quite different. Then to analyze the temperature, and this is weather for Damascus, and you see the whole year, the temperature difference from winter to summer. You see the radiation instead of a middle temperature, month's middle temperature. So you can analyze, is it important to use the solar loads for heating up the building, or you have to shelter it by, for example, a shading device. So then we should analyze the comfort criteria. This is a typical slide. You can see here the temperature and the humidity ratio, and this depends on the comfort. And if you use, for example, a natural ventilated building, you can use an extended comfort zone. And the goal is all these dots should be inside this green area. When the wind is also important, so the wind direction, day and night can be quite different. The situation of a site inside a city or outside a city, that's a difference. For example, also for the temperature inside a building, you have a hot spot. Typically, the temperature is 3 degrees higher than outside the building, outside the city. So that's important for the thermal comfort. And the wind is also, you can see it here by computer fluid dynamic simulation, the wind speed. This is the main wind direction. Red means that we have a high wind speed. Blue means that we have no wind speed. And you can imagine that it's a difference to make an open window here or to make an open blue part. So that means you have no good natural ventilation in the building here, but you have a very good ventilation here. So this is one key aspect for design a building. And to explain a little bit more, I will show you some project from us, starting from a master planning down to the building. I think this is a very famous project. This is the Master City, and this should be the first CO2 neutral city in the world. Okay, the discussion is what is CO2 neutral. I think that's another discussion. But the main goal was to produce energy on site and not to use more energy. And you see it, the design, the master planning design is quite different. Like the design you see it today, for example, in Abu Dhabi or in Doha. You see always high-rise buildings, very expensive buildings, and these are buildings mainly 5 floors height up to 10, and very small streets. And that's a reason, or that's important for design. The first step was to think about how we can, what is the way to a CO2 neutral city project. And you see the 3 steps: load reduction, system optimization, renewable energies. So you can see here the CO2, the orange one, and you see it for UAE, for Abu Dhabi. And you see they use 28 tons per person and year. And to reduce the loads, we are on the level of the United States, nearly 18 tons per CO2 per person. Then we make a system optimization like Germany or Europe, nearly 10 tons per person. And when we use renewable energy, you see we have electrical power, but we can reduce it by 0 by renewable energies. So these are the different steps to come to a CO2 neutral city. Why are the streets so close? This is a photo from Abu Dhabi, from Sheikh Zayed Road. This is a very important road. And you see the outside temperature can be in summer between 50 and 70 degrees. That's very hot. But the perceived temperature, you can see it here. This is a radiant temperature. This is part of a perceived temperature. One example, we have an air temperature of 37 degrees, but we have a radiant temperature of 38 degrees. Because the building has a temperature of 38 degrees, but the streets have a temperature of nearly 60 degrees. Because the sun shines direct on the asphalt. It means the radiant temperature is 48 degrees. So that's not possible to walk there or to stand there. So one important thing is to shade the streets. Here are also some examples. In the desert we have typical, in Abu Dhabi, nearly 70 degrees. In mid of Abu Dhabi the temperature is higher because we have no wind there. So more than 70 degrees. If you reduce the solar load by shading parts driven by the buildings, you can reduce it up to 40 degrees. And with green, with evaporative cooling, down to 38 degrees. Only by the passive design. And not the building design, only the master planning design. And that was the first step to the master planning, to the architect, to say, okay, we have to reduce the streets there to come to a better comfort there. But the result was then, if you have so close streets, it's not possible to drive car there. The streets are too close. But on the other way, if you want to design a CO2 neutral city, you cannot use cars. You cannot use cars there. So we changed completely the traffic concept. We have only some main streets, but typically you have very close streets, and then the traffic is under the streets in level 0. And what is also very interesting is to look what is the historical design of cities, for example, or of a building. This helps you very often to come to a good design. Typically in these hot regions, the grid of a city is rotated by 45 degrees. Why? Because if you have a north orientation, you have sun direct in the streets because the sun stands very high. If you have east-west, you have the same problem because the sun path is directly here. So that means if you rotate the city grid, you have mainly shaded streets there. So that means the whole city is rotated up to 45 degrees. And the result, this is one of three, no, this is a university, different buildings. You can see it. In the first step we saw 37 degrees and the radiant temperature of 48 degrees. Now we have 39 degrees air temperature and the radiant temperature on the street is 37 degrees. So it means it's lower as the air temperature. This is the first step for good design. Here you can see the global concept, the streets there, the streets, only very short streets, because this is the influence of a very hot and humid wind. So the wind cannot go direct in the streets. We have open areas with green to evaporate the wind in winter time, and you see the open streets in this direction because here we have no wind. And totally, it's a balance of different energies. This is, we calculated it for a conventional city. For this city with a conventional design, we have 80% of the CO2 by building design, energy generation, waste and transportation. And with a new concept, we reduced the CO2 emission of a building design to 56%, by renewable energies 24%, waste 12%, and transportation up to 7%. And we produce CO2, it's a heat sink, 1%. That means in the total balance we are by zero CO2. That's a theoretical idea. So in reality, we will see what is the development of the city. Another aspect will be the material, how to use a material and how to change a material. This was one of our first international projects. This is a Bangkok International Airport, and the architect Murphy Yan from Chicago got the first place in the competition, and his idea was to make a glass and membrane roof, single membrane and single glass roof, very transparency. And after the first design step, they analyzed that the building needs too much energy. That was one part. And the second part, they have a lot of problems with condensation outside the building, because the temperature outside the building is nearly 30 degrees and with a humidity of 90%. So that means if you reduce the temperature inside the building up to 24 degrees, you have condensation outside the single layer membrane and glass. So it was not possible to use this design. So the architect had only one chance to change the construction of the building. But he said, I don't want to change the construction because this is very important for me for the design of the building. And then he came to us and said, is it possible to make another concept by the same design? And what we did is, we changed the material, the inside material, we changed the emissivity of a material. Here's a balance. Typical glass or a membrane has an emissivity of nearly 1. So that means if the ceiling is very hot, 35 degrees, they have a high energy transport inside the building. We have a hot radiant panel over here. So that means you can cool down the air to 24 degrees or the floor to 23 degrees. Too many people are dissatisfied with the comfort inside. We change the emissivity of a membrane. You can see it from 1 to 0.2. And only by changing this material, the comfort inside will be by 10%. That's absolutely optimum. This is a low E coating. It's a metal sputtered surface, and you can see it because it works only in the long wave radiation part, not in the visible part. And for example, heat mirror glass has also such low E coating inside, but you can see it. That was the first time we used this one, and we saved only by changing the material 65,000 tons CO2 per year. And the second aspect was now, if it's not so important the temperature there, we can change the climate situation there. That means we reduced the ventilation part only in the zone where the people are walking. So that means the temperature over there will be nearly 60 degrees. And the result was we have no condensation outside the building because the temperature inside in this part of the building is nearly the same as inside. You can see it here. We changed the ventilation concept. We have a displacement ventilation. So we have only cold air here, and we have hot air here. So no condensation there. You can see it here in the simulation. Very hot there, cold there, no condensation there, and we reduce the energy consumption dramatically. This was a mock-up test also. And here you can see what was the result. The result was we reduced the peak cooling load by 35% and the energy demand by 30%. Only by changing the concept, the energy concept, but with the old design. That was very important for our company in this time to show the architect this helps you for your design. And this is not a restriction for your design. This is a picture of a floor cooling system. This was the first time, I think it was nearly 3,600 kilometers tubes lying there. And the company said, it's not possible for us to do it. It's so expensive. Then we said, okay, if it's expensive for you, we will import it from Germany or from Europe. And then it was very cheap. And now it's state of the art with Technik. Very simple technique. Tubes inside, and inside is hot or cold water. Here's some impressions. This is the main hall. These are the different fingers. One aspect was also the low E coating. In this time, there was no company who produces a membrane with a low E coating system. So we evaluated in the world which company can do this one. We got 100 samples of the membrane, and every company said, I have a low E coated membrane, and no one was low E coated. And this was a development with the companies together, the 3 companies, and now it's possible to use this low E coating on the membrane. Another building is a residential building with Stephen Hall Architects in Beijing. There we had also a sustainable approach. What we did is we used appropriate thermal insulation. This time nobody uses thermal insulation in China. We optimize also the glass quality, and we use external shadings. That was absolutely new for the Chinese. And we use also a radiant sealing system. This is a slab heating and cooling system to optimize the radiation part. We have a displacement ventilation to reduce the ventilation. We have a central air conditioning, and we have a high indoor air quality. For example, we use a shaft, a central shaft, and integrated the fresh air and the supply air and the exhaust air. So we can reduce the shaft area. We use the slab cooling system. It's nearly the same as in Bangkok airport from the floor, from the ceiling. We have operable window. We have no problem with condensation because the temperature is much more higher as with as you use ventilation cooling. You see here the heated coil and in the suspended ceiling. We use an external shading device. It's a small metal shading device. You can look through, like if it's closed. And the displacement ventilation, you can see how it's functioning. We use the air there from the floor, a very low speed, and we can reduce the amount of air, and the temperature is only one up to 2 kelvins lower. So very energy efficient. This is part of a slab cooling system. And in the end, it's also important to look to the temperature for the energy production. With the geothermal pipes, for example, we produce water with a temperature of 16 up to 20 degrees directly. So this is a temperature that you can use direct in the slab cooling system. That means this is only a free cooling system with no chiller. And we use the geothermal piles in winter for heating production with a temperature of 45 up to 30 degrees, also using in a slab heating system. And we use with a chiller driven by geothermal piles, air temperature up to 6 and 12 degrees, or cooling water up to 16 degrees. So the amount of energy and the quality of energy is important for the system and for the building. So it means we have no cooling towers. That was one aspect of the concept, no cooling towers. You know, in front of a Macchia you see everywhere the cooling towers, the heat exchangers. We have no cooling towers there because we use the geothermal piles for cooling. We have a very high chiller efficiency, and we have no water consumption, and we reduce the investment cost. In the first step it was the same as in Bangkok. The company said it's not possible for us to use for us a heat pump, and then we said, okay, you can buy it everywhere in the world, and then it was possible. It's always the same way. So the summary is, what are system components? High efficiency HVAC system, displacement ventilation. We use a radiant cooling and heating system. We have free cooling, a very high free cooling potential, and we have a very efficiency energy supply concept. You can see here the boreholes. They are nearly 400 boreholes under the building, in a depth of 100 meters. This is a project finished, I think, nearly 15 years ago. It's a project in Germany. It's a design school in Essen. And this was a competition together with Sana from Tokyo. We did a lot of projects with Sana, and she came to us and said, I have a special idea for this competition. I want to use concrete building, and concrete exposed inside and outside. That's not a problem. That means in Germany you have to insulate between the two concrete layers, because we have in Germany energy code that you have to fulfill, and that means you have to insulate the concrete. So that means to have a three-layered wall, concrete, insulation, concrete. The next one was, she said she wants exposed concrete. That means to have to use more concrete. Also, the facade should support the structure. So that means the thickness of the wall goes up. Inside, she said she wants no columns or only a few columns. But then she said, I don't want a thick external wall. So at this point, you can say it's not possible. But to analyze this special site, this is mid of Germany, and we have a lot of mines there, and we pump the water up because you have to do it because we have problems with the underground. And the water has a temperature of 38 degrees the whole year. And what we said, then we said, okay, if we pump the water from the underground up, we use this water, we use this temperature to insulate with the active water, with the hot water, the wall outside. And additionally, for the column-free rooms, we developed a concrete slab system with a pebble slab. I will show it to you. What does it mean? Here you can see the system. The mines, depth of nearly 1,200 meters with a temperature of 38 degrees. And they pumped it up and put it in a river. And there we use a heat exchanger and use the temperature to heat up the external walls. Because we don't use the water up to now. And it was very helpful that the mine where we pumped the water up is not so far from the site there. And it's nearly the same as a concrete or slab cooling system. We have the tubes inside the concrete. We have a layer outside and inside, totally 300 millimeters. And we reduced the heat loss by heating up the wall. A very simple system. Very simple. But everybody said it doesn't work. So what's important? Important is to analyze the critical parts of a construction. This is a connection from a window to the concrete. So it means we have to analyze exactly what is the minimum distance to the window to reduce the condensation inside the building. But here you can see what is the result. Typically we have a very thick wall construction, and with ours construction a very thin layer, and we have no problems with condensation inside. Here you can see the temperature from inside to outside. You can see it here, 20 degrees inside, when the insulation and the outside temperature is nearly minus 10 degrees. And with the active system, we have inside the temperature and falling down, and here is the problem with the condensation inside the insulation. And with our construction, we never have a problem with condensation in this construction. It's very simple. So, it was important to do it very exactly. You see the red tubes, plastic tubes with water inside, different openings, windows and doors. And this is a section of a bubbled deck. This is a concrete slab with our slab cooling and heating system. And these are plastic bubbles inside filled with air. It's a recycled material, you can see it here. The tubes for heating and cooling, the bubbles filled with concrete. So the weight of, you can reduce the weight very, very good by using these bubbles. So that was the idea of Sana'a in the competition, a very wide room, only some columns. This is an elevator part, in top of the building the office elements. This is a picture in the construction. You can see it's not white, they changed it because it was too expensive. But in the end, the result, I think it's much more better because it's a rough structure and not a white structure. And everybody said, this is much more better. You see the openings, yeah? You see it, the openings more in the edge of the building. So that means you use good concrete for the structure there. And this is a result from outside. And if you're standing outside of a building, you say, oh God, what is this? 5-storage building with a lot of windows there, partially openable. And if you go near of a building, you see the result of small layers. Only 30 centimeters by 5 storage. And it looks like paper. And that was the design of Sana'a. I said, I want a very thin layer facade. And that was the result. And with the energy concept, we supported this design. Without the energy concept, it is not possible, or it was not possible to build this building there. And after they finished the building, the people came to us and said, oh, guys, you are very crazy, but you can use the energy from the mines, for example, for heating up residential houses. Yes, that's true. But you need, we call it light tower projects, to show the people to think more about using potentials on the different sides. This impression inside, no shading device, only a little bit, because we have very high thermal mass. So, and some other examples of buildings, there are, especially me working, I'm working on some different stadiums worldwide. We did 2 stadiums in Manaus, in Fontenova, last World Championship, and this was the aspect of outdoor comfort. Yeah. How can we consider it? This was a project in Abu Dhabi to optimize the construction. This was the same discussion. Should we use a very expensive material to reduce the solar loads, or can we use a very simple system? And in the end, our result was we can use a double layer membrane with a low E coating inside, nearly the same as in Bangkok. We did some ice rings, and also we did some different projects with very high atria. This is the garden by the base in Singapore. If you're in Singapore, go inside, it's a very amazing project. Inside the the highest atrium, we have a hill there with a cloud, where we produce the artificial cloud. And to optimize the concept, we developed, for example, together with our engineers, a new measurement to measure the comfort inside the building in aspects of direct radiation from the sun. And last but not least, we're doing also a lot of internal clouds. To do this, you have to understand the physics of a cloud. So that means think about temperature, think about humidity. And this was our first cloud. It was 2002 in Frankfurt, Leiden building. This is a fair, a very small cloud, but you can go through with the elevator to the cloud. And it was important to have the cloud in mid of the atria to go through the cloud. This was the Biennale 2010. This was a very big cloud, 800 square meters. You can see it here. You can go through a ramp, through the cloud, up to the cloud. And our newest project is in the theater in Munich. We produce, from the beginning up to the end, a cloud over the persons here. I think this is also a good example to show climate engineering or the integrated design process helps you in the design. And this is not a restriction. Okay, so I'm at the end and I'm open for some questions. Thank you.